So the goals, we want to be able to distinguish between nuclear fusion and nuclear fission. A lot of times those are thrown around carelessly as being very similar or being almost the same thing. They're actually quite different. So you need to be able to distinguish between those two and their uses. It says you need to understand the concept of half-life, including determining the ages of objects based on radioactive isotopes. So a lot of times what they'll do is they'll find some sort of leg bone from like a horse, and they say, "Oh, this horse was 20,000 years ago," and they want to know how they figure that out. And how they do that is they use radioactive isotopes. So that's kind of one of the things we want to look at as well. And you need to be able to write and balance nuclear equations for alpha, beta, and gamma decay, and any other sort of nuclear reaction as well. You need to understand the principles that are involved with that. Chemical reactions. So chemical reactions are ones in which the protons and the neutrons remain constant. So in other words, the nucleus is untouched. Okay, so since the nucleus is untouched, the only thing that can change are electrons. Now, chemical reactions is what we're going to study for the majority of this year. But for now, we're going to look at something called nuclear reactions. But just know that chemical reactions are ones in which only the electrons react. So they share electrons, or one takes another electrons. But when we're talking about nuclear reactions. We're saying stuff that happens in the nucleus. So this right here is going to change, and that normally doesn't happen. So that's going to change. So if we look at what we have here, we have a larger nucleus right here. We have protons, neutrons, and electrons, but all of a sudden something leaves. So we had something leave the nucleus, and whenever it leaves the nucleus, that makes it a nuclear reaction. So whenever we say nuclear, we mean we're changing something in the nucleus itself. A fission reaction. A fission reaction is one in which you start with a larger atom. Okay, usually it's something pretty big like uranium or plutonium or something along those lines. Now, I didn't draw all the protons and neutrons in plutonium and uranium because it would be a whole bunch in order for that to work. So, if you take a look at this, fission reactions are lower in energy. By when I say lower in energy, they are still very, 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 very energetic. Okay, so yes, they're lower in energy than fusion, but they're still very, very, very energetic. In fact, you only see them in nuclear power plants and early nuclear bombs. So, like Hiroshima, Nagasaki, those sort of early test bombs and bombs that were used in World War II were examples of fission reactions. Now, when we look at the next thing, we have fusion reactions. So fusion reactions are when you take two smaller nuclei, so you've got two nuclei, you slam them into each other as hard as you can, and whenever they do, they can stick together. If they stick together, that's what we call fusion. Now, fusion is something that we haven't mastered in terms of control yet. The only fusion reactions that we're aware of are thermonuclear bombs, which are our high yield nuclear devices, and the sun. We haven't been able to control fusion in a sustained reaction. If we could, we'd have almost free, cheap, abundant electricity, but we haven't been able to do that quite yet. All right, so we come to our first radioactive decay. Now, radioactive decay is when you take something and you split it apart, like we were talking about before. So we have a change in the actual particle itself. So if you look right here, it says alpha decay is what happens when you emit an alpha particle. That's why it's called alpha decay. Now, an alpha particle is a helium nucleus. So this right here represents the alpha particle. And that's something that you need to know. So whenever you say alpha decay, I don't want you to draw an alpha particle. I want you to actually draw it as a helium. Now, the reason why it's called an alpha particle is it is a helium nucleus. There are no electrons associated with it, so we don't really call it helium. But what we have here is a nuclear decay. So if you look, I start off with polonium. This polonium turns into lead. And whenever it turns into lead, you can kind of look at the numbers here. So I have 207, or excuse me, 211 and 207. And then I have this 4. So what you'll notice is I have 211 on the top, and then I have 211 on the top when you add those two numbers together. Now when you take a look at the next one, bottom, bottom, and bottom, you have 84 on the left and you have 84 on the right. That's kind of a hallmark of what we talk about, these balanced nuclear equations. We're going to get into that a little bit later, but just know for now that an alpha decay is when you eject a helium nucleus. Here's our helium nucleus, and it's ejected from the original atom. We also have beta decay. Beta decay is a little bit different because it's a little bit more complicated. You actually have a neutron that turns into a proton and an electron and something called an antineutrino. So a neutron has a slightly heavier mass than a proton, and that's because it's really a proton and electron kind of combined together. So if you were to look at this, when we undergo beta decay, what you'll see that the mass number stays the same. This top number, I have 210 on the left, and I have 210 on the right. And then I have a 0 particle and a 0 particle. So those right there, you've got 210 and 210. So the mass of whatever undergoes beta decay remains the same. But what happens is it actually becomes a different element. If you look right here, you have this 82 number. But I'm taking one of the neutrons and I'm turning that neutron into a proton. So this mass number doesn't change because remember this is the sum of the protons and the neutrons, so that remains constant. But then what you have to do is you have to add a proton to this and it actually changes the element. Now, if you remember before we had the numbers on the left and the numbers on the right had to equal. And that's okay because remember an electron has a value of -1. That's the charge value. So when we put our -1 here, you have 83 minus 1, and that's 82, and so we still remain balanced. Now this thing right here called an antineutrino, a lot of times that's left off, but you do need to know that it's there. It's a very, very, very small subatomic particle that we may get into a little bit towards the end of the year. Next you have gamma decay. Gamma decay occurs when the nucleus is really, really, really high in energy. Okay, so the nucleus itself, so let's kind of take a look at it. The nucleus itself, a lot of people think of the nucleus as, hey, it's stuck right here and all the electrons are moving around it. And while the electrons do move much, much faster than the nucleus still does spin. It rotates, it moves translationally, it does move. So whenever you take a look at this nucleus has an energy state. If you were to take and spin it faster, if you were to spin it a whole lot faster, or you to make it move this way, what we say is that nucleus is unstable because it has so much energy that it doesn't want to have. So what we have is we have an unstable nucleus. What you have is we indicate that by this star value. So that means it's more energy or unstable. Well, it wants to be stable. So what it does is it gets rid of that energy. But the thing that's missing from this nuclear equation is where did the energy actually go? And so you actually have to add plus a photon. Okay, that's a particle of light. We've talked about it. So that's a particle of light that gets kicked out, and you do need to include that. We have it right here on the bottom picture, and you need to put it in the equation as well. Now, photons don't have any mass, and they don't have any charge, so they don't cause anything to balance, but you do need to know that it's there. So whenever we balance these nuclear equations, there are two rules that we're looking at. The first one is the conservation of mass. So mass on both sides have to be equal, which we see is our original example for alpha decay. So you've got a 211 as my mass on the left, and 207 plus 204 is my 211 mass on the right. When I take my 84, that's my conservation of charge. That's my atomic number, and that needs to be constant as well. And then I have 82, and I've got 2 on the other side, which is 84. So that's what you do whenever you balance a nuclear equation. So even if you're given a nuclear equation that doesn't have anything to do with alpha, beta, or gamma, if you use these two rules, the idea of conservation of mass and conservation of charge, which are two big, big laws that we'll talk about not only in this class but in physics, then you can balance any sort of nuclear equation. So this is example A1. It says the exact mass of helium has been determined experimentally to be 4.002602. Is this number consistent with the data provided below? And we want to justify our conclusion. So the very first thing we want to do is we always want to come up with our conclusion, what the answer is going to be. So what is our conclusion? And then we want to find some sort of evidence in the question. And then we want to give our reasoning or our justification. Okay, so the first thing we need to do is we need to find the answer. So if you should know that a helium-4 atom is composed up of 2 protons, 2 neutrons, and 4 electrons. That's what a helium-4 atom is. 4 is indicated by the total of the protons and neutrons. The fact that it's helium means that there's 2 protons. So what we can do is we can take this neutron number and we can multiply it by 2. We can take the proton number and we can multiply it by 2. And then we can also take the electron number and we can multiply it by 4. When we add those values up, we want to compare it to our original value. So what we do is we get our calculator out and we multiply 2 times 1.00727 64668, and then we add 2 times 1.00866491156. You hit enter right away, not even accounting for the electrons, you get a number that's 4.03188. So already this number right here is greater than that number right there. Now you may be thinking, well, that's crazy. It's supposed to be conservation of mass. It is true, but when you get into higher level physics and chemistry and those sorts of things, you'll start to realize that mass and energy are the same thing. So what happens is we get something called the binding energy. So some of the mass is converted to energy, and it's called the binding energy of the nucleus. It's what holds the nucleus together. Example A2 says a uranium atom undergoes alpha decay. Write a balanced nuclear equation that predicts the product. So we want to take a look at this, and what we do is we see this alpha decay. So the first thing that we know that we can do is we can write a alpha particle, which is a helium, in the product. That's the easiest thing. It's the thing we can do right away. We know there's going to be something else besides the helium there as well, and we're going to have to account for that, but we do know this for now. It says that we have a uranium-235 atom. So the first thing we want to do is we want to say, okay, well, we know uranium is the symbol U. We know that 235 represents the mass. Now, we can use the periodic table to look up what the periodic table would say for uranium, and that's 92. And now we can use the law of conservation of mass and the law of conservation of charge or atomic number, and we can see that this is going to be 231 and 90, and you should be able to predict the product from the periodic table based on that. Now if you noticed, 235, 4 plus 231 is 235, 90 plus 2 is 92, 92. You should be able to say that is conservation of mass upheld in the nuclear reaction? Yes, you should be able to say that conservation of mass is upheld, but this equation still fails, and you should be able to find the source of the failure, why this is not a balanced nuclear equation, even though conservation of mass is upheld. So now we look at radioactive decay in a little bit more detail. It turns out that radioactive decay actually occurs in regular intervals. So it's something called half-life. And so half-life is the time it takes for half of the radioactive material to decay to a more stable state. Now something that you should realize is that this is an average. Okay, it doesn't mean, hey, I've got 2 particles and in exactly one half-life I'll have 1. What it means is that on average, if you have 2 particles, it'll reduce to 1 in a certain amount of time. Okay, it's not an exact number. Instead, it's an average. It's really important to understand. What it's basically saying is that if I have 10 particles, that these 10 particles are unstable, and so what they want to do is they want to turn into circles. But in order to do that, they've got to undergo some sort of radioactive decay, and that takes time. So in one half-life, you'll have 5 circles, and you'll have 5 X's left over. Okay, after another half-life, you'll have either 7 or 8 circles, and you'd have the leftover would be X's. So after each half-life, you're reducing the half that you had before. And you see that this is our example. Alpha decay would be an example of radioactive decay. Carbon-14 is probably one of the most famous for these radioactive decay because you can use it to date any sort of organic matter. Anything that was organic has carbon in it, and carbon to a certain percentage has carbon-14. Most carbon is carbon-12, but about 1% of the carbon is carbon-14, at least in the atmosphere. So what you do is you have something that's alive. So you have something like a tree. Here's our tree, which doesn't look like a tree, but we've got our tree. And then you can say, okay, this tree is exchanging carbon with the atmosphere. So it takes in carbon dioxide and it expels oxygen and it loses carbon to growth and all kinds of things. But it's exchanging carbon with the atmosphere. Well, when the tree dies, it can no longer exchange carbon with the atmosphere. So what happens is 1% carbon dioxide, 1% carbon-14 goes down. And based on the amount of carbon-14 that's left in a fossil, you can tell how how long ago that organism died. Based on how long ago it died, you can then guess how old it was to begin with. Turns out that carbon 14 has a half-life of about 5,730 years. So you can get a pretty good estimate for how old things are based on that. Here's a half-life graph. So the first thing you realize is that it says number of C14 molecules, but it's in millions of atoms. And then you have time, but it's in years. It's really important that you always check the scale. So whenever you're doing this, you kind of start at your starting point, and you want to draw as smooth a curve as you can down. Okay, to reach that last point. That's not a great part right there, but you see our smooth line as we have possible. It's not connected dots, but it should be a relatively smooth curve. So whenever you do this, this allows you to predict how many molecules are left at any given point. So let's say if I were to ask when do I reach 40 million molecules, I can just come across and come down, and I could say, hey, I would reach 40 million molecules, I don't know, somewhere around 7,000 years after we start. So it's a way of you being able to estimate and figure out how many molecules are left based on the graph. This actually gives us our half-life equation. The half-life equation says the number of molecules that you have are equal to how many you started times this factor right here. This factor is based on two things. It's based on the half-life of the element, and it's based on how much time has elapsed. Both of those things are time. So if you realize time divided by time is going to cancel out and give you no units. But you see right here where n is the number of particles, and that's how many that you have right now. So it's remaining. You have NO, which is the original number or starting number of particles. T is how much time has passed, and the half-life is a number that doesn't change for the element. So in this one it says potassium 40 has a half-life of 1.277 billion years. It says a scientist suggests using potassium 40 to analyze the earliest human remains believed to be 100,000 years old. Confirm or dispute this decision using the clear method. So we want a conclusion, we want some sort of evidence, and we want our reasoning. So the first thing is the evidence in this case. You've got 1.277 billion years and you've got 100,000 years. Okay, so we know this is the evidence that we're going to use in order to say whether it's good or whether it's bad. And our reasoning in this case is going to be the equations. Yes, your reasoning can be an equation. In fact, an equation works perfectly well for reasoning. So our equation is n equals NO times 1/2 raised to the t divided by t to the 1/2. So if we were to take a look at this, you have the half-life is 1.277 billion years. So it's a very, very, very large number. Even this, 100,000 years divided by a billion is a really, 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 really small number. So whenever you take 1/2 and you raise it to this very, 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 very small number, you should realize that this small number is going to become approximately 1. It's actually like 0.9999999 something, but it's about 1. Well, if you take 1 and multiply it by your original number of particles, you have the same number of particles. So if you have no difference in the number of particles, is this a good test to use? And the answer is, of course, no. No, this is not good because of these two things. Because its half-life is 1.277 billion and it's only been 100,000 years. And your reasoning would be the equation, the fact that when you do this, you get the same number of particles. On this one it says, how long will it take for the atom to reach 25 million atoms of C14? So the first thing we want to do is we want to establish where 25 million atoms are. So we take this is 40 and this is 20, so we go halfway, and that's our 30 mark. And we want to go halfway between 20 and 30, and if you look, that actually matches up perfectly with a data point. So we take that and we go down, and we can say it's probably somewhere close to maybe 11,000 years. It's kind of hard to tell with this kind of a marker, but then let's say if it was something a little bit different. Let's say if it was something like 70 million. Well, 70 doesn't get to a data point, so this is where drawing the curve actually is really important. So you've got to be able to take this and you've got to be able to draw a relatively smooth curve that goes through and allows you to kind of see where everything is. Now, that's not a great thing. The computer can do it much better than I can. But when you see it this way, this gives you a little bit more detail as far as being able to draw the lines down and saying, hey, that's probably something like maybe 2,000 years or something along those lines. So it's really important that you be able to do these things and draw the curve and then be able to estimate from there. This one says the half-life of a pizza has been determined to be 3.5 minutes. How long will it take to consume 87.5% of the pizza? So when a pizza first gets there, half of it's gone really quick because people are hungry. They all grab a slice and they eat it. And then after they eat it, they're not quite as quick to get another slice. And then they're not quite as quick to get another slice. So how long will it take to consume 87.5% of the pizza? It should be about 10.5 minutes, and you should be able to figure that out entirely on your own.